Welcome to the next installment of Advanced Chemistry Lectures. In this series, which is the second lecture in the more basic coordination chemistry series, I'm going to focus on phosphine ligands, Bent's rule, and their application to transition metal complexes. And in fact, this is going to be part one of a two-part series. And in the last lecture, which was focused on hard, soft, acid, base theory, I made note that soft-soft interactions in transition metal chemistry are extremely important. And some of the softest ligands we're going to encounter are going to be phosphine ligands. And phosphine ligands are really important in transition metal chemistry. And so before I even start talking about transition metal complexes or the metal atom itself, you kind of have to focus on what's around the metal center to really understand how the metal center is going to behave. And so first I'm going to do is review soft acids and soft bases. If you're really interested in hard, soft, acid, base theory or need a review, go to the previous lecture. But when we're talking about soft acids and soft bases, what we're really focusing on is polarizability of these atoms. And so soft acids are traditionally very large transition metal centers with low oxidation states. This renders them quite polarizable. Their electron cloud can be manipulated quite easily. Look at some of the softest acids we have here. We have silver plus, gold plus, mercury 2 plus, platinum 2 plus. All of these transition metal atoms are large. They have large d electron counts. In this case, either 10 or 8 d electrons, and they're all quite large. The only one here that's really not that large is copper 1 plus. Copper 1 plus is first row transition metal element, but it's D10. It is often also quite soft. Well, soft bases, what you're really thinking about is low electronegativity. And if you remember from my last lecture, I said, remember, S goes with S. And so if you have soft bases, typically you have thiols, very soft donors. They have low electronegativity, also like iodide, and any ligand that has pi bonds. Remember, pi bonds are quite polarizable in general. And in fact, this lecture, though, we're going to really focus on phosphine ligands. Phosphine ligands are really important soft ligands to transition metal atoms. And so when we're talking about now a soft acid and soft base combination, we're really talking about a lot of donor-acceptor synergy taking place. Remember, soft-soft interactions are quite covalent in nature. And so if they're quite covalent in nature, they're going to be sharing electron density. And so carbon monoxide is a ligand we often focused on in inorganic chemistry, and phosphine ligands behave very similar to carbon monoxide. They're both sigma donors. They both have a lone pair on the donor atom. In this case, phosphorus has a lone pair. The carbon atom has a lone pair. They donate in a sigma fashion into an empty sigma type orbital on the transition metal center. This could be a dz squared orbital, that's what I've drawn here, or a dx squared minus y squared orbital. Carbon monoxide is also a very potent pi acceptor, and it accepts electron density into its anti-bonding pi star orbital. You can see that here, in which a d pi orbital on the transition metal center is able to funnel electron density in a pi fashion into the anti-bonding orbital on CO. Well, phosphines behave quite similarly. They are also pi acceptors. However, they're now accepting electron density into a sigma star orbital, and the orbital interaction is a little bit more challenging to draw. And so if I treat the R atom here, R group on phosphorus, let's say that's a hydrogen atom. If that was a hydrogen atom, it would be a 1s orbital. Well, if this was now out of phase with the lobe on phosphorus, I'm going to indicate it right here. They are now out of phase with one another. That is the sigma star anti-bonding combination. The transition metal atom can now donate electron density to that orbital on phosphorus, resulting in the pi acceptor capability. But notice what's really most important about this is the soft-soft interactions. They are sharing electron density. Phosphorus is giving electron density to the metal, and the metal is giving electron density back to phosphorus. And this type of interaction is critically important in catalysis. Many of the most important soft-soft pairings of a Lewis base with a Lewis acid are responsible for very important catalytic reactions. And so I've drawn three really catalytic species here. Some are intermediates, but notice here in the case of alkane dehydrogenation, you have an iridium 1 center. The iridium 1 center is D8. That is a soft, low oxidation state. Big iridium atom ligated now by soft phosphine donors and a soft carbon donor. Wilkinson's catalyst, which is quite famous, Usually known for hydrogenation, features a rhodium-1 center that is also D8, and it is ligated by soft phosphines and a kind of borderline chlorine atom. And then we have palladium catalyzed cross coupling, in which you usually have in an intermediate that is very much resembles this, a low coordinate intermediate in which palladium is palladium 0, which is D10. It's quite soft, and it's ligated by a very soft phosphorus donor. In this case, it is a Buchwald ligand, a bi-aryl dialkyl phosphine, quite soft. This is responsible often for the initial oxidative addition of an aryl halide. And so these soft-soft interactions are critically important in catalysis, and it's because phosphine ligands are so important. We really need to understand a lot more about them. And so if you take in general chemistry, which I think everybody has, you may think, well, it's just a heavy analog of an amine. But we already know from the previous lecture, they are in fact quite different. Remember, amines and water here, these are very hard ligands. They're highly electronegative. Once you go down one row of the periodic table, we talk about phosphines or thiols. These are incredibly soft ligands, and so there's already that fundamental difference. But what about the structure? Well, we know both ammonia and water are approximately sp3 hybridized. The lone pair on nitrogen occupies more space, and so the HNH angle contracts to approximately 107 degrees. The two lone pairs on water occupy a lot of space. That further contracts the HOH angle to approximately 104.5 degrees. And these are sp3 hybridized. But how can you actually view the hybridization? Well, remember that nitrogen, if you have a nitrogen atom, it has 5 valence electrons. It has a doubly occupied 2s orbital and 3 singly occupied 2p orbitals. When it hybridizes, it forms 4 sp3 hybrids, one of which contains the nitrogen lone pair shown here. So now you have 3 singly occupied sp3 hybrid orbitals. Well, the hydrogen atoms can come along. The hydrogen atoms all have a single electron and a single 1s orbital. There's 3 of them. That results in pairing of all of those electrons, and now nitrogen contains an octet, and ammonia is an extremely stable molecule. Well, what about the heavier analog? What if we talk about phosphine? Well, phosphine is way different than ammonia. First and foremost, phosphines, PR3 molecules, in this case pH3, they are not hybridized. The pH bonds are formed between the 3p orbitals on P and the 1s orbital on hydrogen. How do we know that? Well, look at the bond angle. The H-PH bond angle is approximately 93.5 degrees. Remember, the p orbitals are all orthogonal to one another. They are mutually perpendicular to one another. They are 90 degrees apart. And so almost all the bonding is composed of the p orbitals on phosphorus overlapping with the 1s orbitals on hydrogen. And what that does, it makes the lone pair on phosphorus, which I'm indicating here, contain a large degree of s character. It is largely localized in a 3s orbital. And so this is actually true of all 3-coordinate phosphines. In fact, also for low-coordinate P as well. And so if we think about imines and pyridine, which I think everybody is familiar with, those nitrogen atoms are sp2 hybridized. Well, if they're sp2 hybridized, you can think of it as sp2. That means it's s1. One s orbital is now hybridizing with 2 p orbitals. And so by orbital composition, that means it's 33% s and 66% P. Well, notice the lone pair on the individual nitrogen atoms here. The orbital composition has been calculated, and you'll notice that is almost exactly as predicted. You would predict the lone pair to be 33% S, well, the 33% S and 66% P, and that in fact is borne itself out in calculations. Well, the second you jump to the heavier analog now, we talk about phosphalkenes or phosphonine. The HPC angle in a phosphalkene is approximately 110 degrees, and the CPC angle in a phosphonine is approximately 100 degrees. I might have said 110 degrees, I meant 100 degrees. They're both approximately 100 degrees. And so what that means is they contain a lot more P character. The angle is approaching 90 degrees. It's 100 degrees, but that's a lot closer to 90 degrees than it is to 120 degrees. And what you'll notice is that the orbital composition of the lone pair has been calculated as well. And notice what this means. The the electrons in the 3s orbitals are almost entirely of s character, over 60% s. And that makes sense. Well, if the bonds are mostly p, that means that the lone pair then has to be mostly s. And so this is what we're really going to focus on in this lecture, some of the consequences of Bent's rule. And Bent's rule links hybridization with electronegativity. And Bent's rule, summarized by Bent himself in his papers here, notice the early 60s, that atomic S character tends to concentrate in orbitals that are directed toward electropositive groups. When I look at that statement, I think, man, this sounds like Old English almost. You know, what does this actually mean? And so I like my definition better. My definition is that electronegative substituents suck up P character. Electronegative substituents concentrate P character. And so before we even get into that, let's focus a little bit on the s orbitals and the p orbitals, because we kind of have to understand them a little bit to understand structure, bonding, acidity and basicity, and other chemical properties. And so if we focus now on s and p orbitals, you know that there is one s orbital, one 2s orbital. If we're now talking about, we're on the second row of the periodic table, and we're talking about now two p orbitals, you know that there are three 2p orbitals. They are dumbbell-shaped. They are mutually perpendicular to one another. But what else do we know? Well, a 2s orbital is closer to the nucleus. Electrons in 2p orbitals are farther from the nucleus. And this is really, really, really important. And the reason this is so important boils down to a very, very rudimentary understanding of Coulomb's law. Remember that Coulomb's law, if we're talking about in terms of potential energy, and we're talking super qualitative here, the potential energy is equal to the distance between two charges here. And so Q1, that's right, represents the nucleus, and Q2 represents an electron outside of the nucleus. Well, the closer, the distance here is represented by R, the closer they are to one another, the more negative the potential energy is going to be. The more negative the potential energy is, the more stable the molecule is, the more stable the electron is. And so if you have two oppositely charged particles, here we're going to be talking about the positively charged nucleus. The second charge is the electrons outside of the nucleus. The closer those two charges are to one another, the more stable they are. The lower the potential energy, the more negative the potential energy, the more stable those electrons are going to be. And a consequence of this is that the electrons in s orbitals are lower energy than the electrons in p orbitals. And another consequence of this fact that electrons in s orbitals are lower in energy than electrons in p orbitals is due to electronegativity. And so remember now, the closer you are to the nucleus, the more the electrons are going to be pulled towards the nucleus. And remember, electronegativity is the measure of an atom's ability to attract or pull electron density towards itself. And so now, if the electrons have more S character, they're closer to the nucleus, they're going to be more electronegative. And so if we just take simple hydrocarbon examples, here we have methane, CH4. You already know it's sp3 hybridized. Here we have ethylene. You know that each carbon atom is sp2 hybridized. And here we have acetylene, and you know each carbon atom in acetylene is sp hybridized. Well, think about it now in terms of S versus P character. If it's sp3, you can think of it as S1p3, and therefore it is 25% S. S1p2, it is 33% S. SP, it is 50% S. The more S character you have, the closer you are to the nucleus, the more the electron density is going to be drawn towards the nucleus. The more S character means you are going to be more electronegative. And in fact, we fundamentally already understand this. You know from organic chemistry that alkynes, like acetylene, have very acidic CH bonds. And why do they have acidic CH bonds? They have acidic CH bonds because there is a large degree of S character in those CH bonds. The more S character in the bond, the more acidic that CH bond is going to be. And so why is that? Well, if you deprotonate acetylene, here it's deprotonated, that's its conjugate base. That lone pair now is in an sp hybrid orbital. If it's in an sp hybrid orbital, those electrons now are closer to the nucleus. If they're closer to the nucleus, they're more stable. If the conjugate base is more stable, that means the acid was more acidic. And so we now have the more S character that is in an individual CH bond, the more acidic the molecule is going to be. Furthermore, if we now look at the JCH coupling constant, so we're now focusing on the CH bond here on methane, the CH bond here on ethylene, the CH bond on acetylene. The more S character that is present in the individual bonds, the higher the coupling constant. And the reason for this is similar. The more S character that's in the bond, the closer those two atoms are to one another, the closer the nuclei are to one another, the more those nuclei are talking to one another, the more they're talking to one another, the closer the distance, the larger the JCH coupling constant. Furthermore, since this is all tied to electronegativity, we know now that the more S character you have in the individual bonds, the more acidic you are. Well, this also makes sense. Remember, we know that methyl groups are electron donating, and so if I now put an H atom at the end of all of these, we know now that we know a methyl group is in fact electron donating. Well, this also makes sense. This carbon atom is sp3 hybridized. It's not very electronegative at all. It's donating electron density. As the S character increases, now we go to this aldehyde. You now are 33% S. It starts to pull electron density towards the carbonyl. Well, if you now are sp hybridized, like here in the case of a cyanide group, you're now pulling electron density towards the cyanide group. It's highly electron withdrawing, and therefore the electron density is being funneled towards the cyanide group. That renders this hydrogen quite acidic, which you already know HCN is a potent acid. And so the more S character in the individual atom, the more S character in the hybridization, the more electronegative that atom is, the more electron withdrawing that is. And so what's the consequence of this? A real consequence of this is that all CC and CH bonds are not the same. And often people think of them as being the same. Take, for example, methane or octane. 1, 2, 3, 4, 5, 6, 7, 8. All right, both of those are alkanes. They are both completely non-polar molecules. They have no dipole moment whatsoever. Well, if you increase the S character in the individual bonds, like let's say this carbon atom, it is now 50% S. Well, look how much more electronegative it is than an sp3 hybridized carbon atom. This would be an sp3 hybridized carbon atom. Well, now you have an electronegativity difference of almost 1. You have an extremely polar covalent bond. Electron density is being funneled towards the alkyne. That leads to a strong dipole moment, and methylacetylene is in fact a polar molecule. Same with phenylacetylene. Here you have an sp2 hybrid carbon atom bound to an sp hybrid carbon. Well, notice how much polarity is present in that bond as well. Phenylacetylene is also a polar molecule. Furthermore, even toluene has a dipole moment. You may not expect it, but toluene is in fact a polar molecule. There is polar character in it. It has a dipole moment. And so it's now all CC and CH bonds are not the same. You have to focus on the hybridization because the more S character that's present in the individual carbon atom, the more that's present in individual bonds, the more electronegative those bonds are. And what even further brings, another property of all of this is that all CC single bonds are not the same. And you may have realized this. Well, if we take the 3 examples I've shown here in the upper right, we have ethane, we have propylene, and we have methylacetylene. Notice that the CC single bonds start to decrease in their length. In ethane, it's 1.54 angstroms, which is normally cited as a carbon-carbon single bond. But now, if one of those carbon atoms is sp2 hybridized, like this one, notice that the CC bond length shrinks. If you now get an sp hybridized carbon atom, the bond will shrink even farther. And that's because, remember, the more S character that's in the individual hybridization, the closer those electrons are to the nucleus, the shorter the bond distance is going to be. And so as the S in character increases in the bonds, the bond length will decrease. Notice the extreme example here is highlighted as entry 6 is in a diene, in which now you sort of have a conjugated system here in which you have 2 sp hybridized carbon atoms, they are now a diene. Those are alkynes, but the individual carbon atom here is a CC single bond. Look how much that bond length dips. It dips to 1.38 angstroms. That's just a slightly longer than, in fact, the CC double bond in ethylene. The more S character in the individual bonds, the shorter the bond length. And so now let's focus on other atoms beyond carbon. Well, go back to Bent's rule here. Here's another way he's phrased Bent's rule. If we're now talking about, let's say, atoms outside of carbon, an atom tends to concentrate its S character in the orbital or orbitals occupied by unshared electrons, lone pairs, as the electronegativity of the substituent increases. Again, I feel like I'm reading old English. I like my definition better. That electronegative substituents suck up P character. All right. So let's focus on ammonia and water, and now the effects of swapping those H's for F's. And notice I've highlighted those bond angles in pink in the table. And so as you go from ammonia, which you know has a bond angle of approximately 107 degrees, if you swap those H's for F's, look how much the bond angle decreases. Well, electronegative substituents suck up P character. So the fluorines are highly electronegative. They're sucking P character towards them. If you're sucking P character towards yourself, the bond angles are going to start to approach 90 degrees. If the bond angles start to approach 90 degrees, what that means is that leaves the lone pair with an increasing amount of S character. Notice the exact same trend plays itself out in water, H2O versus OF2. Fluorine is sucking up a P character. As it sucks up P character, the bond angle now decreases to approximately 103 degrees. That increases the S character in the lone pairs. Well, is there a way to now add S character to the bonds? And you can. If you have methyl groups, we just learned methyl groups are electron donating. Well, methyl groups, as you know, swap these individual H's for methyl groups. Remember, methyl groups are large. Well, what that does is it spreads the angles out. Notice as you add methyl groups, the individual angles get bigger and bigger. Well, if the individual angles are getting bigger, you're adding S character in those bonds. Remember, if you think of sp hybridized as being 180 degrees, that's as much S character as you really can get in there, 50% S. You're starting to get the angles get bigger and bigger. And so methyl groups add S character. Well, if methyl groups add S character, that is going to increase the bond angles. It goes up in the case of trimethylamine, goes up to 109 degrees. In the case of dimethyl ether, up to 111 degrees. So you're adding S character in the bonds. What that does is it makes the lone pair have more P character. If the lone pair has more P character, it is going to be more basic. And so now let's look at the conjugate bases of the original system we talked about. We talked about methane, ethylene, and acetylene, and we talked about the fact that acetylene was our strongest acid because the CH bond had the largest degree of S character, which was 50% S. And we talked about the weakest acid was methane. It is sp3 hybridized, and therefore its percent S character is 25%. That meant it was the weakest acid. Well, now if we look at the conjugate bases, you know that methyl minus is an extremely strong base, right? Methyl lithium is methyl minus. Methyl lithium is an extremely strong base. The more P character in the lone pair, the stronger the base. And in fact, we can use this exact same argument to answer the question, which of the following nitrogen species is the strongest base? Well, if you look at acetonitrile, that's now 50% P in the lone pair, and you've really never seen acetonitrile behave as a base. You have seen amines and pyridine appear as a base. Well, an amine is 75% P, and therefore it should be a pretty strong base. Pyridine is 66% P, and therefore it is a weaker base. The strongest base here is an amine. It has 75% P character in the lone pair. The more P character in the lone pair, the more basic the more basic that species is. And so a question I love to ask to graduate students, mainly because they usually get it wrong, is what's more basic, an amine or a phosphine? And you should be able to answer this question now because you know that phosphines are not hybridized. And so if we're focusing on amines, what we know is that the nitrogen center is sp3 hybridized. What that means is that now the lone pair is 75% P. And so it's looking pretty basic. Well, a phosphine, what we know now is that the RP bonds here are composed largely of P character because phosphines are largely unhybridized. What that does is it means that this is an S-type lone pair with a large degree of S character. The more P character in the lone pair, the more basic the atom is or the molecule is, and that is why amines are typically much more basic than phosphines. And again, the reason for that is the lone pair on nitrogen is approximately 75% P. On the other hand, phosphines are unhybridized. The P center is not sp3 hybridized. That means the RP bonds are largely composed of P character. You know that by the very narrow angles. That leaves the lone pair with a large degree of S character. More S character means less basic. All right, and so what other properties does this lead to? Well, amines versus phosphines, you may, depending on who is your organic chemistry professor, you may talk about inversion barriers at nitrogen and phosphorus. And if you did, what you learned is that nitrogen has a very low barrier to inversion. It's on the order of 7 kcals per mole. And what this means is that nitrogen rapidly interconverts at room temperature. And so if this is an R nitrogen center in the sense of absolute configuration, that means this would be an S center on nitrogen. And what you know is that nitrogen, stereogenic at nitrogen, and so chiral N doesn't really exist because of rapid racemization. And so the reason that amines are so easily able to invert or racemize at room temperature is because they are sp3 hybridized. If they are sp3 hybridized, the bond angles are approximately 109.5 degrees. We know in the case of ammonia, it's 107. But in order to invert at the nitrogen center, you need to go to an sp2 hybridized transition state. What that means is the nitrogen atom ends up, or the nitrogen lone pair ends up in a pure p orbital. It then flips out the back, and you get your inverted nitrogen. Well, traveling from 109.5 to 120 and traveling back to 109.5 does not require that much energy. It requires 7 kcals per mole. Well, in the case of phosphorus, what we know now is that it is not hybridized. The lone pair is largely composed of S character. The PR bonds are composed largely of P character, and so it takes a lot of energy to phosphorus to access the transition state. Remember, the transition state is sp2 hybridized P center. That means the lone pair is in essentially a 3p orbital. And so from traveling from 94 to 120 and travel back to 94 requires a lot of energy, and in fact, it requires 30 to 35 kcals per mole to invert at the phosphorus center. And what that means is that phosphines are configurationally stable at room temperature. You can isolate P stereogenic phosphines. And probably most importantly, in 2001, Bill Knowles won the Nobel Prize in chemistry, or shared part of the Nobel Prize in chemistry, for the isolation and application of dipamp towards the synthesis of L-DOPA, which is a Parkinson's disease medication. And so he was able to synthesize P stereogenic phosphines and apply it towards the synthesis of enantiopure pharmaceuticals. And so this is the reason, now the reason being that phosphorus is unhybridized, that it has such a large barrier to inversion. All right. Well, since phosphorus doesn't hybridize, there are other consequences of its lack of hybridization, and of course there is. Well, phosphines are known to act as pretty good nucleophiles, and notice back in 1960, very simple reaction shown up here, a tertiary phosphine quartonizing, and so undergoing an SN2 reaction with ethyl iodide to give you a phosphonium salt, an I minus. Well, this chemistry really is, I would say, as expected in a lot of ways. Alkyl phosphines, very electron-rich phosphines, react quite fast. That's this region up here. Electron-poor phosphines with electron withdrawing groups like cyanide react pretty slow. They're down here. But what's less obvious is that bulky phosphines react faster than less bulky phosphines. And that's kind of counter what you learned in organic chemistry, right? Really good nucleophiles, they're kind of like spears of electron density. They can get right in there and react quite fast. These big bulky groups don't actually act as nucleophiles that well. They tend to act as better bases. And so in this case, though, bulky phosphines react faster than less bulky phosphines. And so why is that? Well, this also goes back to its lack of hybridization. And so if you consider the extreme case of totally unhybridized pH3, in which now all of the PR or pH bonds, let's say they're composed entirely of P character. They're 90 degrees to one another. Well, what that means then is the lone pair is entirely of high S character. Well, the extreme in the opposite direction would be the groups around phosphorus are so large that the P center actually flattens out and becomes sp2 hybridized. If it completely flattens out and becomes sp2 hybridized, the lone pair is then going to have high P character. Well, the more P character it has, the more basic it is, the more nucleophilic it is, the farther those electrons are away from the nucleus, the higher the potential energy. And so now if we use this exact argument to explain the difference between triethylphosphine and tricyclohexylphosphine, you can see why tricyclohexylphosphine is so nucleophilic. Well, the ethyl groups are quite small. And so now the CPC angles are approximately 100 degrees. That means they have a large degree of P character. And what that does, it means the lone pair has a large degree of S character. Well, as you incorporate cyclohexyl groups are quite large. Therefore, the CPC angles start to increase. They increase to almost 110 degrees. What that means is that there is more S character in the bonds. If there's more S character in the bonds, there's more P character in the lone pair. More P in the lone pair. The more P you have in the lone pair, the more you look like this, the more you look like a sp2 hybridized center with a lone pair and a p-type orbital. The more nucleophilic you are, the more nucleophilic you are, the more P character in the lone pair, the faster you're going to react with electrophiles. And so that's why tricyclohexylphosphine reacts faster than triethylphosphine with electrophiles. The second reason, which I like a lot and is closely related, is what we're going to talk about in the next couple slides. The second phosphorus quartonizes, it becomes 4-coordinate. It makes 4 bonds. It will become hybridized. It will move to nearly sp3. Well, if you start at 110, in the case of tricyclohexylphosphine, in order to get to tetrahedral, you have to only reorganize by less than 1 degree. In the case of triethylphosphine, you start at 110 degrees, you're going to have to reorganize to 109.5 degrees. That's a large amount of reorganization. It's going to take longer for that reaction to occur. And so tricyclohexylphosphine is more reactive than triethylphosphine towards electrophiles because its lone pair contains more P character. The large cyclohexyl groups occupy more space. That increases the CPC angles. The larger the CPC angles, the more S character in the bond. That leaves more P character in the lone pair, makes it more nucleophilic. The second reason is now once it becomes 4-coordinate and hybridizes to sp3, very, very, very little reorganization is necessary. If very little reorganization is necessary, the reaction is going to occur faster. And so I've already answered the title of this slide, does phosphorus ever hybridize? And it does, yes. It hybridizes when it becomes 4-coordinate, when it forms its 4th bond. And this was discovered really quite early on, comparing the IR spectra of dimethylphosphine with its borane analog. And what you'll notice is that the pH stretch of the free 3-coordinate phosphine is 2292. When you put a borane on there, the pH bond gets stronger. Its stretching frequency now increases almost by 100 wave numbers. And even in 1964, right here, key statement directly from the paper, stronger pH bonding for 4-coordinate P might be found in rehybridization of phosphorus bonding when a 4th atom is attached. It's exactly what's going on. The second you form the 4th bond, and that 4th bond can also be to transition metal centers, phosphorus goes sp3. This phosphorus center right here is sp3 hybridized. The second you go to sp3 hybridized, you increase the S character in individual bonds, more S character, shorter, stronger bonds. And so about 16 years ago, very similar phenomenon was observed. These ferricenyl methylphosphines, as they're called, are a very interesting class of phosphines. They're actually air stable, even if R is H. Those are air stable primary phosphines. If you look at the pH stretch of the free phosphines indicated here in green, you'll notice they're approximately on the order of 2,300 wave numbers. Well, the second you add a borane to them, notice that the pH stretching frequency increases by almost 100 wave numbers, and that's because the phosphorus center becomes sp3 hybridized. Another consequence of that sp3 hybridization, look at the pH coupling constants. They go way up. The reason they go way up is that in the 3-coordinate phosphines, if these R's are H, those are now unhybridized, roughly unhybridized pH bonds. Well, if they're unhybridized, they contain a large degree of P character. The second you quartanize and form the phosphine borane, you increase the amount of S character in the individual bonds. More S in the bonds means larger JPH coupling constants. More S in the bonds, larger JPH coupling constants, and stronger pH bonds. And so you can actually even see this with very basic MBO calculations. And so if you look at the free phosphines, indicated here as compound 2 and 3, look at the composition of the pH and PC bonds. They have a huge degree of P character. They're both greater than 80% P. They're largely unhybridized, these free phosphines. Look at the lone pair. In both cases, the lone pairs are greater than 50% S. But the second you quartanize at the P center, you add the boranes, shown here. Look what happens. You go to approximately sp3 hybridized. The degree of S character in the individual bonds increases greatly. Notice that the lone pair is now complexed by a borane. You go from largely S character to predominantly P character. There is a reorganization of electron density. There is a rehybridization. On quartanizing, phosphorus goes to approximately sp3. The bonds now get increasingly strong. They have more S character. This is critically important. And really important because phosphines act as really good donors to transition metal centers. I'm really going to focus on this on part 2 of this lecture. But with what we know now, remember, bigger phosphines are better nucleophiles. They're better donors. They can be better bases. And so if we look at the table here from Tolman, Jacks, 1970, what you'll notice is that tritert-butylphosphine is the best donor. It has the smallest CO stretching frequency. Trimethylphosphine is a far poorer donor. The smaller the CO stretching frequency, the better the donor is. We'll get to that concept more, but tritert-butylphosphine is a much better donor than trimethylphosphine, even though they are both trialkyl phosphines. And the reason for this is exactly what we talked about. If you think about trimethylphosphine, it's kind of like a very unhybridized P center. There's lots of P character in the CPC bonds. If there's lots of P character in the bonds, that means the lone pair has a large degree of S character. Well, tritert-butylphosphine, you start to splay towards 120 degrees at the P center. The tert-butyl groups are super large. That flattens out the phosphine. If the phosphine was totally flattened out, it would be sp2 hybridized. The lone pair would then be in a p-type orbital exclusively. That means it's going to be a really good donor, really good nucleophile, and in fact it is. It binds extremely well to transition metal centers, dumping electron density onto the metal center and acting as an extremely good donor. The last thing I want to talk about in terms of Bent's rule and phosphines in general, and even you're going to see some hydrocarbons, is the effect of rings. What do rings actually do? Well, if you think about rings, they introduce strain. And so a question I love to ask graduate students on their cumulative examinations is the one shown here. Which of the following does not react with methyl iodide? Explain. Okay. So this is a phosphorane, this is a phosphatane, and this is a phosphylane. And so when you have a 3-membered ring, you just think of it like a triangle. The angles are approximately 60 degrees. All right, they're actually less in a phosphorane. But in order to get to 60 degrees, I view this as like an extreme amount of P character in the ring. Remember, 90 degrees is maximum P character. If you're below 90, you're making an extremely strained system. You're pumping P character into the ring. Well, if you're pumping P character into the ring, the lone pair then is going to have a huge amount of S character. The S character is going to increase greatly. As the ring gets less and less strained, there's now going to be more S in the ring. If there's more S in the rings, because the angles are opening up, that means the lone pairs are going to have more P character. Well, if they have more P character, they're going to be more nucleophilic. So phosphoranes here are the example now that they do not react with methyl iodide. The lone pair contains such a large degree of S character because all the P character is in the ring that this lone pair is now largely non-nucleophilic. If it is non-nucleophilic, it is not going to be reacting with methyl iodide, and that it does not react with methyl iodide. In a similar fashion, a lot of times this question is asked: why is the pKa of cyclopropane so much significantly lower than these other hydrocarbons? And so here we have methane, cyclopentane, cyclohexane. The pKa's of those CH bonds are on the order of about 50. Well, it drops significantly when you get to cyclopropane. So why? Well, cyclopropane, remember these angles here are 60 degrees. You're pumping a huge amount of P character into the ring. What that does is it leaves the CH bonds with more S character. The more S character in the individual CH bonds, the more acidic those molecules are. We talked about this when we focused on acetylene. Remember, acetylene, the carbon atom is sp hybridized. That CH bond you learned in organic chemistry is extremely acidic, can be deprotonated by things like sodium amide. The more S character in the individual CH bonds, the more acidic the molecule is. And so in the case of cyclopropane, huge amount of P character gets pumped into the three-membered ring. That leaves a huge amount of S character in the individual CH bonds. More S character in the bonds means more acidic. And then a kind of a related question that I love to ask as well is, why does adding methyl groups weaken CH bonds? And so if we focus on methane versus ethane, methane versus ethane versus, let's call it isopropyl H versus tert-butyl H, notice that the bond dissociation energy decreases as you go down that series. Well, why is that? Well, remember, methyl groups add S character to the bond. And so the more methyl groups you put in, here's 1, here's 2, here's 3, there is more S character in the individual CC bonds. If there is more S character in the CC bonds, that means there is more P character in the CH bonds. The more P character in the bond, the longer the bond, the weaker the bond. And that's why this call it tert-butyl H, has a bond association energy of the CH bonds almost 10 kcals per mole less than methane. Methyl groups add S character to bonds. 3 methyl groups add a lot of S character to the CC bonds. That results in a lot of P character in the CH bond. More P character, higher potential energy, weaker bond, and the dissociation is much easier. And so to summarize everything we talked about, some of the most important properties of phosphines. Remember, unlike their lighter analogs, amines, which are sp3 hybridized, phosphines are unhybridized or largely unhybridized. The lone pair has a large degree of S character in it, rendering the R-P-R bonds with lots of P character. You see this by phosphine has approximately H-pH bond angles of 93 degrees. However, the second you add a Lewis acid, that Lewis acid could be a borane, it could be an alkyl group, or it could be a transition metal center, which we're going to talk about more in part 2 of this series. The phosphorus center goes 4-coordinate. When it's 4-coordinate, it adopts sp3 hybridization. You add S character in the individual bonds. The bonds get stronger. The individual, if R is H, you would see this by an increase in the JPH coupling constants. Phosphines, again, they're unhybridized. The bigger the phosphine, in the case we talked about triethyl versus tricyclohexylphosphine, the larger the R groups on phosphorus, the more the R groups move away from each other. Think about cyclohexyl here. The cyclohexyl groups spread themselves out. That increases the CPC angles. The larger the CPC angles, the more S character in those bonds. The more S character in those bonds means there's less P character in those bonds. The P character then resides in the lone pair on the phosphorus center. The more P character in the lone pair, the more reactive, the more basic, the more nucleophilic, the better the donor it is. If we talk about rings, small rings, there's lots of P character in the individual rings. What that does is it means you have high S in the lone pair. As the ring size opens up, you add S character into the rings. What that does is it means there will be more P in the lone pair. And so the more P in the lone pair, the more nucleophilic the phospholanes are as composed to their three-membered phosphorane counterparts. And then the final thing is that phosphines, remember, they're excellent Lewis bases. They're excellent ligands. They're soft. They exhibit this donor-acceptor synergy. They form covalent bonds with transition metal centers. They give electron density to the metal as a sigma donor. They accept electron density in a pi fashion. They're just like CO. We're going to see this bear itself out more. It's extremely important. Soft metals with soft bases like transition metals like palladium, platinum, with soft bases like phosphorus, very covalent in nature. They're sharing electron density. And this is going to be extremely important. In part 2 of this, I'm going to focus more on now how phosphorus binds to transition metal centers. Now you know a little bit about their behavior. Now we're really going to focus on how they bind to transition metal centers. And so I hope you look forward to part 2 of this lecture. I will hopefully upload it soon. And I hope you learned something.